Welcome back to the podcast where we dive into the intriguing world of distributed databases. Today, we're focusing on a vital topic, replication and the challenges it presents. Replication is all about copying data across multiple servers to ensure that information is reliable and readily available. But, as you might guess, this process isn't without its quirks and complexities. So let's unpack some key concepts related to replication, including the anomalies it can cause, the guarantees it offers, and how different configurations can affect user experience. First off, let's talk about replication lag. Picture this. You're scrolling through comments on a social media post. You see a comment appear only to have it disappear moments later. That confusion stems from replication lag, which is the delay in updates propagating across different replicas. For example, if user 2345 reads a comment from user 1234, they might initially see it. But if they then read from a stale replica, that comment could suddenly vanish. It's a disorienting experience, almost like time is moving backward, and it highlights the importance of ensuring what we call monotonic reads. So what exactly are monotonic reads? This concept guarantees that once you see newer data, you won't go back to seeing older data in subsequent reads. While it's not as strict as strong consistency, it's certainly an improvement over eventual consistency. This ensures that if you're reading from the same replica, your experience remains stable, preventing the confusion of seeing data revert to an earlier state. Now let's touch on causality and the issues that can arise from it. Imagine a conversation between Mr. Poons and Mrs. Cake. If Mr. Poons asks a question and Mrs. Cake responds, there's a clear causal relationship. But if an observer hears Mrs. Cake's answer before the question due to replication lag, it creates a strange scenario where it seems like she has psychic abilities. This violation of causality is another hurdle in distributed systems, especially when different replicas are out of sync. To help mitigate these kinds of anomalies, databases often provide consistency guarantees. For instance, if writes happen in a specific order, reads should reflect that same order. However, in partition databases where different segments operate independently, achieving this can be quite tricky. Without a global order of writes, users might encounter some data that's outdated while other parts are current. When designing systems, it's crucial to think about how users will react if replication lag increases significantly. If users can handle some lag without feeling frustrated, that's a win. But if it leads to confusion, developers should aim for stronger guarantees, such as read after write consistency. It's important not to mislead users into thinking that replication is synchronous when it's actually asynchronous, as that can lead to significant issues later on. Transactions play a vital role in databases, providing stronger guarantees that simplify application development. While single-node transactions have been around for quite some time, many distributed systems have moved away from them due to performance and availability concerns. However, this perspective can be a bit too simplistic, and we'll dive deeper into transactions in future episodes. In many replication setups, there's typically a single leader node that handles writes, while follower nodes replicate the data. This leader-follower model works well, but if the leader becomes unreachable, write operations can come to a halt. Multi-leader configurations, where each node can accept writes, offer a solution, but introduce their own complexities, particularly when it comes to conflict resolution. In a multi-leader setup, each data center can have its own leader, enabling local writes that are asynchronously replicated to others. This can enhance performance by reducing latency, since writes don't need to travel to a central leader. However, it also raises the challenge of managing write conflicts, especially when multiple changes to the same data occur in different data centers. Let's consider a practical example. Imagine an application where users need to access and modify data offline, like a calendar app. Each device acts as a local leader, allowing for independent writes that sync later when online. This scenario illustrates the complexities of multi-leader replication, as the synchronization process must handle potential conflicts and ensure data integrity. Collaborative tools, such as Google Docs, further highlight these challenges. They allow multiple users to edit documents simultaneously, which resembles multi-leader replication, but requires sophisticated conflict resolution mechanisms. When two users make conflicting edits, the system must detect and resolve these conflicts seamlessly to avoid disrupting the user experience. As we've explored today, replication in distributed databases is a double-edged sword. While it enhances reliability and availability, it also introduces challenges like replication lag, violations of causality, and conflict resolution. Understanding these concepts is crucial for both developers and users as they shape how we interact with distributed systems. As we continue our journey through the world of databases, we'll delve deeper into transactions and explore alternative mechanisms in future episodes. Thanks for tuning in, and we hope you'll join us next time as we unravel more complexities of distributed systems.